Okay, so let's walk through this NMR question. We've got two parts to it. We've got state why TMS, CCl4 and CDCl3 are used in NMR spectroscopy, and explain how their properties make them suitable for use in NMR. This is marked using what they call levels of response. You've got to go through 3 stages to get all of the marks. I think the best way to answer this is by grouping them together. We're going to talk about TMS on its own, and then talk about CCl4 and CDCl3 together. Let's begin by looking at TMS. So we just remember what it looks like. Silicon at in the middle there, and then we've got 4 methyl groups around it. So it's important that we start off by answering the first part of the question, state why it's used. So TMS, we can say, is used as a reference. Other words you can use would be a standard, or to calibrate the spectrum. And then we can then go on and answer the question why it's used, explain how its properties make it a good reference, for example. Okay, so we look at the structure. What we notice is that we've got 3, 3, 3, 3, so 12 protons, and they're all in the same chemical environment, so they're only going to give 1 peak. And also because there's nothing electronegative in here, the silicon's quite electropositive, so there's nothing that's de-shielding these protons, so they're all going to be shifted to a low chemical shift upfield to the right. Okay, so they're going to be far away from other peaks. So let's talk about those two things. TMS is used as a reference. We can say that it has 12 hydrogens in an identical chemical environment, which therefore gives a single peak, and we say that peak is away from where you might expect the other peaks in the spectrum to come. Of course, you could say that this peak is shifted to the right or shifted upfield, if you like. Okay, so we also need to say a few other things perhaps about this. One being the idea that it's inert, so won't react with your sample, and the other being the idea that it's volatile, therefore easier to remove. So we can say that TMS is inert, therefore won't react with the sample. And it is volatile. Therefore easy to remove. Okay, so we've dealt with that, and we are well on the way to getting our 6 marks. Now I want to talk about the tetrachloromethane and the deuterated chloromethane there as well. So firstly, it's important that we identify what they're used for. So the first thing I would say is that to just state quite explicitly that both of these are used as solvents. So CCl4 and CDCl3 are used as solvents. Okay, and now we're going to say why, and we're going to talk a little bit about the polarities. So if I just quickly draw them out, just very simply. So CCl4 looks like that. Yes, the CCl bond is polar, but you've got 4 identical bonds, so the polarities effectively cancel each other out. So this is going to be non-polar. CDCl3. If I draw this differently, maybe just to give you an idea, using the dashes and wedges. We can use the idea that this is polar because of this CD bond. That's not really a polar bond at all, but these three are. So effectively, we've got this idea that at the top here we've got a non-polar bond, and then towards the lower half of the molecule we've got these three CCl polar bonds. So you've got that kind of mismatch. So you do have polarity here. So CdCl3 is polar, CCl4 is non-polar. So we're going to use that idea here. Okay, so we don't need to explain why, we just need to say that they are. So CCl4 is polar, therefore this would be used for dissolving, CCl4 is non-polar, I should say. Okay, so you'd use that to dissolve non-polar organic molecules, whereas CdCl3 is polar. So if you had polar organic molecules, things like alcohols, maybe carboxylic acids, then you'd use this instead. And then the other idea is that both of these do not have any hydrogens, therefore wouldn't give any signals in proton NMR. Okay? So we can say this, and both do not have any hydrogens, so would not give a signal in proton NMR. Okay, so there we go. Try to answer it systematically, say exactly why each of them is used, and then explain the properties. Okay, next part, question B. So deduce the splitting pattern, so just the splitting pattern for each of the peaks given by the hydrogen atoms labelled X, Y and Z in the hydrogen NMR spectrum of the compound shown. I think it's always a good idea to draw this out. Maybe do the displayed formula so you can see everything really clearly. So a CH3 to start with, then I've got a CH with a chlorine, then I have a carbon with an oxygen, then a CH, so that's a carbonyl, and then I've got a C with a H and then two methyls, so C with a H and then two methyl groups. Well, if we're doing displayed, we might as well do it all the way. Okay, and now it's important to identify the hydrogens that it was talking about. So X would be these three, and then Y would be this H here, and then Z would be okay, so it's the all of the hydrogens in the two methyl groups over here. So these guys and these guys. Okay, fine. Right, so let's do this then. So X, let's have a think. These are the protons labelled X, and we're thinking about this splitting pattern. So remember in NMR, the integration ratio tells you how many hydrogens responsible for them, so we're not looking at that. The chemical shift tells you something about what they're bonded to, and we're not talking about that. We're talking about the splitting pattern. The splitting pattern is found by looking at the adjacent carbon, so not this carbon, the one that they're bonded to, but the adjacent carbon. What is bonded to that? We've got one H bonded to the adjacent carbon to hydrogens X. So use the N+1 rule. We would have a doublet. Okay, because these three hydrogens are coupling to this hydrogen here. There's only one of these hydrogens there. Apply the N+1 rule, so 1 + 1 = 2, hence a doublet. Okay, let's do the same thing, but now let's do it for hydrogen Y. Again, we look at the carbon it's bonded to, and now we're looking at the adjacent carbons. There's nothing on the carbon, or no protons, I should say, on the carbon to the right. So we must therefore look to the carbon to the left. Here we've got 1, 2, 3. So this hydrogen here is coupling to 1, 2, 3 hydrogens. Again, apply the N+1 rule. So 3 + 1 is 4. so a quartet. Okay, and then the same analysis for protons labeled Z. So all of these guys here, they're on this carbon and that carbon. So we're looking at the carbon adjacent to both of these, which is this carbon here. This carbon here only has one hydrogen. So all 6 of these are coupling to just this one hydrogen here. So if they're coupling to one hydrogen, apply the n+1 rule. 1 + 1 is 2, so a doublet. Okay, now we've got to suggest why it is difficult to use table B in the data sheet, which I've got here, to predict the chemical shift value for the one labelled Y. So the one labelled Y is here, and we can see that it's bonded to a carbon next to a chlorine and a carbon next to a C double bond O. The problem with that is in our data book we have two ways of looking at it, really. So if I want a hydrogen next to a carbon bonded to a chlorine, that would be this range here, but I've also got a hydrogen on a carbon next to a carbonyl. That's in the data sheet as well. That is up here. Okay, so really it's the idea that the group that we've got doesn't fit with this, because we've got you can think of it as being it's yes, it's this, but it's also this as well. So what should I do? Okay, so it doesn't really fit. We don't have an exact match for it in our data sheet. Okay, so what we can say in our answer is that the hydrogen labeled Y is bonded to a carbon next to chlorine and next to a carbonyl, so C double bond O. Right, therefore doesn't exactly match the data book. Exactly. Okay, we might be able to estimate it from the data booklet, but it doesn't give you an exact kind of range. Okay, so we turn over. We've got one more question on this particular, or one more part of this particular question. So 2 isomers of this each have 2 singlet peaks only in their proton NMR spectra. In both spectra, the integration ratio for the 2 peaks is 2:9. Deduce the structures of these 2 isomers. A tricky one. If we only have 2 singlet peaks in proton NMR, that means that we've only got 2 proton environments. Okay, so we're going to use that fact, and we're going to use this 2:9 to help us as well. The 2:9 is interesting because what we can do using the 2:9 idea is we can group them. If you've got 9 protons responsible for one of these environments, then we can kind of think, okay, well, I've got 2 CH3 groups and I've got another CH3 group over there. Now that equates to 9 protons. So I think it's a good assumption that all of those are going to be responsible for one of these environments. Okay, because that gives you the integration of 9. And then the other 2 protons, so this one here and that one there, we can group them together and say, all right, they're going to be responsible for the other environment with the integration of 2. So if we can therefore have the 3 methyl groups in one environment and the 2 protons in another identical environment, then we might be able to have 2 different isomers. Okay, so this might need a little bit of work on extra paper, but hopefully we should be able to come up with 2 ideas here. Okay, so first of all, what I said was I wanted to get the 3 CH3s into one environment. So I'm going to do that to begin with. So on a carbon here, what I'm going to do is I'm just going to put the 3 CH3s. So in doing so now, I've got one identical environment because everything from here on in is going to be something else. So all of these will be chemically identical. Let's just see what else I've got in my formula. So I've got that CH3, and I've got, sorry, these two CH3s, this CH3 as well. I've got the carbon there. So I've got maybe two other carbons to identify. So I've got one there, and I've got another one as well. I've got two hydrogens, a double bond O and a chlorine to fit in somehow. So if we use the idea that we want to keep the two hydrogens identical as well, what we can do is just manipulate that a little bit. So one idea would be this: if we just put the two hydrogens here, so there and there, and then we can have the double bond O and the Cl here. So we've got this acyl chloride. So if we just check, so the 3, 6, 9, we've got 9 protons there, all in the same environment. Integration ratio would be 9 for them. These two hydrogens here, chemically identical, and 2 of them, so integration of 2, that would work. We can then use a variation of this where we just have the same principle to begin with. So put all of your methals on a single carbon. And now what we're going to do is we're going to kind of just mess around with this slightly. Rather than having the two H's on here like we did before, I want to have the two H's on this carbon here, but still have them chemically identical and keep everything else the same, if you like. So what I'm going to do is I'm going to swap the double bond O with the two hydrogens. So I'm going to have the double bond O here, and then the two H's there and there, let's say, and the chlorine. Okay, so if we think about these 9 protons here, they're chemically identical, they're all bonded to the same thing there. These 2 protons here, there's 2 of them, which is good, that's the integration ratio sorted, and they're chemically identical because each of these is bonded to a carbon bonded to a chlorine on that side, and then C double bond O, etc. on the other side. Same for that. So there we go. NMR question walkthrough.